Hey guys, alright, so in this video I want to talk about exponential decay, and I'll look at a specific example where we talk about radioactive decay. Okay, so for exponential decay, or radioactive decay, so for exponential decay, there's a similar formula that we have for something, for a function that's like undergoing exponential decay. And it's really similar to the formula for exponential growth. So the formula that I'm going to write down is y of t equals a, where a is some constant, times e to the negative kt. Okay, so the key difference between the exponential growth formula that we wrote down and the exponential decay formula is just that I put a negative here in the exponent in front of the k. So in the exponential growth formula, there was no negative sign. Okay, so I'm doing this just to stay consistent with our course text, which also uses a negative sign there. Alright, so next I want to write down what each of these quantities represents. Okay. So A is the initial amount. So A is the initial amount, or initial quantity. K, which is another constant, this represents the decay rate. So K represents the decay rate. T represents time, just like before. And then y of t, is the amount of the substance that's left at time t. So y of t is the amount of substance left at time t. Okay. Alright, so there are certain elements that are radioactive. So what happens is over time they decay and they split into pieces. So over time we end up with less and less of the quantity of that element that we started off with. That's why we say that element decays, or that substance decays. Okay, so y of t here is going to represent the amount of that substance that's left at time t. Okay. Alright. So what I want to do an example, but before I do the example, I want to define what's called the half-life. The half-life of a substance. Okay. So I'll do this example in a sec, but next I want to define what's called the half-life. Alright. The half-life, so the half-life of a substance is the amount of time it takes for half of it to decay, or in other words, for half of it to be left. So this is the amount of time it takes for half of it to decay. Okay. Alright, so different substances have different radioactive substances have different half-lives. Some of them decay very quickly, some of them decay very slowly. Alright, so what I want to do is I want to do an example where we get a little bit more comfortable with this term half-life and understanding what it means exactly. Okay, so the example says if the half-life of a substance is 7 years, how much of the substance is left in part A after 7 years, in part B after 14 years, and then in part C after 21 years. Okay, so part A says how much of the substance is left after 7 years. So if the half-life of the substance is 7 years, that means in 7 years, half of it decayed. All right, so after 7 years, half of it is left. So after 7 years, 1/2 of it is left. So what that means is, like, if we started off with something like 100 grams of the substance, after 7 years, we'd have 1/2 of the 100 grams. We'd have 50 grams. Okay. Part B is saying how much of the substance would be left after 14 years. Okay. So if 14 years have passed, that means first 7 years passed, and in 7 years, 1/2 of the substance decayed. Over the next 7 years, so this will complete the 14, 1/2 of what was left decayed. So that means 1/2 of 1/2 is left. Okay, so after 14 years, this means this is another 7 after the first 7. So after the first 7, 1/2 of it was left. After another 7 years, so this is after 14 total, now 1/2 of the 1/2 is left. So the way I'm going to write that is I'll say 1/2 of half, which is 1/4 of it. So for example, if we started with if we started with 100 grams, then after 7 years, half of it is left. So 50 grams is left. After another 7 years, okay, so after another 7 years, only 25 grams is left. So overall, that's 1/4 of what we started with. Okay. All right, so finally, we have part C. So part C is asking, after 21 years, how much is left? Okay, so after 7 years, 1/2 of it was left. After another 7, so this is after 14 total, 1/2 of the 1/2 is left. So that's 1/4. After 21 years, 1/2 of the 1/4 is left. So 1/2 of 1/4 is 1/8. So 1/8 of it. 1/8 of it is left. Okay. Alright. Alright, I want to look at another example now. Alright, so this example says that the half-life of an element is 20.5 years. If we start with a 300 gram sample, how much of the element of the sample that we have will be left after 45 years? Okay, so to start this off, we'll begin with our equation for exponential decay, which is y of t equals a times e to the negative k t. Okay, and then what the question says is, it tells us that we start off with a 300 gram sample. So A is the initial amount. So A is 300. Okay, so we can take that and we can plug it in. So if I do that, I get y of t equals 300 e to the negative kt. Alright. And then what it says is the half-life of the element is 20.5 years. So if I plug in 20.5 in for t, if I plug in 20.5 in for t, so if I do that, I get 300 times e to the negative, so plugging in 20.5 for t, so negative 20.5 k. When I plug in 20.5 for t, I should have half of what I started with. So I started with 300 grams. So I should have half of that, which is 150. So this thing right here, y of 20.5, this is 150. It should be half of 300. Okay, so this equals 300 e to the negative 20.5 k. Alright, so now I want to figure out what k is. So next, we'll divide both sides by 300. So if I do that, the 300s cancel over here. On the left-hand side, 150 over 300, that becomes 1 over 2. So 1 over 2 equals e to the negative 20.5 k. Alright, so now we have this exponential equation. I can convert this to log form. So in log form, we'll get log base e, which is ln. The thing that goes inside of the ln is the 1/2. And then the exponent is what goes on the other side of the equal sign. So negative 20.5k goes on the other side of the equal sign. Alright. So now if I get k by itself, I'm going to divide by this negative 20.5. And if we do that, we get k equals, okay. Okay, so if I divide by negative 20.5, I get ln of 1/2 on top. And I'm dividing that by negative 20.5. Alright, so that's what k is. Alright, so now that we know what k is, we could take this and we could plug it back into our equation for y of t. So if we do that, we get that y of t equals 300 e times e to the so if I plug in this k value into here, notice that, so we have negative k, so negative ln of 1/2 divided by negative 20.5. So I'm plugging in k, t. Okay, and then if we simplify this, we have a double negative here, so that becomes a plus. So we get y of t equals 300 times e to the now plus ln of 1/2 over 20.5 t. Okay, so we get this. Alright. What we wanted to know in this question is how much of the substance is left after 45 years. So to figure that out, I just need to plug in t equals 45. Alright, so if I plug in t equals 45, then what we get is we have 300 times e to the ln of 1/2 divided by 20.5, and then times 45. Okay, so we can work this out using a calculator, and if we do that, we get that this is approximately 65 point, and I'm going to round it to 3 decimal places. That gives me 65.512, and the units that we had were grams. Okay, so that's our answer here. One thing that I want to point out about this is, if you guys have web work questions like this, and you guys are entering stuff like this into web work sometimes is picky about the number of decimal places that it wants you to enter in. Sometimes it'll want you to enter in like 4 decimal places. Sometimes it'll ask you to enter in 5 decimal places. So I'd enter in a lot just to be on the safe side.